All right, everybody, welcome to office hours. So today it's going to be a little weird. I'm actually outside, so if you hear some noises, that's kind of where it's coming from. So today we're going to do this warm-up question. We're going to just review all of Sn1 and Sn2 considerations, and then we're going to move on to E1 and E2 and finish up chapter 9. Okay. So the first thing I want to talk about is like what is the main background behind all of this. It's always important to know really what's going on behind the scenes. So let me just pull up this document for you guys. Okay. So essentially, we're going to fill this out as we go. So if you guys have pieces of paper at your house, like just take it out. Sorry, I just have to let my cat in 1 second, guys. So essentially, the definition of Sn2 is a bimolecular reaction where bond breaking and bond forming occur simultaneously. Okay, so I guess what we'll say is this, that bond breaking / forming, okay, occurs simultaneously. Okay, such that the departure of the leaving group we know is facilitated by that incoming nucleophile. So incoming, I'll just write this in parentheses, incoming nucleophile, we know displaces that leaving group. Okay, so we're dependent on that leaving group. We're dependent on that nucleophile. Okay, so is everybody clear on the Sn2 definition? It's a bimolecular nucleophilic substitution reaction where the bond breaking and forming occurs all in that, that concerted step in the beginning, and where that incoming nucleophile is capable of displacing that leaving group. Okay, so on the contrary, for Sn1, bond breaking between the carbon that bears the leaving group is complete before that incoming nucleophile comes in. So I'll write that in words. So essentially, bond breaking occurs first. And that is independent, I'll just say in parentheses, independent of that nucleophile, okay? And I think that should make sense, okay, logically. Like remember, Sn1, we had that leaving group leave on its own. It was kind of limited to secondary and tertiary substituted leaving groups. And that, leaving group that left would be stabilized because, we had a decently, hyperconjugated carbocation intermediate. Okay, so these are the two main definitions for Sn1 and Sn2 conditions. Okay, so that's kind of it for there. So next we can consider kinetic considerations, okay? And this is back to Gen Chem, so I know you guys may not be familiar with this, but essentially, we know that this is bimolecular, right? And let me just draw like a generic, Sn2 reaction up here. So that would be something like, maybe this halide, and we're subjecting it to, maybe NaCN, and we're doing it under like this solvent, this aprotic solvent. So we know that based on the above definition that bond breaking and forming occurs simultaneously. So that means that the rate constant, or the rate law for this, should be rate is dependent on some sort of constant, K, which we don't know, and it's proportional to the concentrations of that starting material, so this halide, which is, to the order of the first power. And then we also have that, concentration dependency of the incoming nucleophile. Okay, so this is really important to understand here, that the rate law is bimolecular, and that's, apparent by the sum of the individual orders. So, the total order here is 2. You just add up those orders, 1 + 1 is 2. So you can tell that this is a bimolecular reaction based on the rate law we wrote, because we're dependent on the concentration of your starting material and the concentration of your nucleophile. In contrast, let's just say we had this example. Okay, so we have a more substituted example, and we're going to just say, let's just say it's water. We're going to do, this hydration example. And, this situation that, leaving group leaves on its own, so we're not dependent on this, nucleophile at all. Really, the rate law is dependent on some sort of constant K, and then just the starting material, okay? So that would be to the first power. So the total order equals 1. Okay, does that make sense? So you just have to be able to write these rate laws potentially. Just know that it's always, for Sn2, it's two things. It's the concentration of your starting material and the nucleophile, whereas in Sn1 conditions, it's just the concentration of your starting material, because we know those mechanistic errors. That should all make sense, okay? So that's that. In terms of stereochemical considerations, for Sn2, we have this trigonal bipyramidal transition state. I'll just put TS, okay? And that leads to what we'll call the inversion of configuration. okay? So let's just kind of like draw, I guess, a scheme of that. So essentially you might have, let's just say this. So we have, I'm just gonna call this R1. You might have R2, and let's just go with, I don't know, this proton, okay? And then we have our incoming nucleophile coming in, okay? So that's gonna basically form a bond here, and then there's going to be this leaving group that also leaves, okay? So this is my transition state. This is the trigonal bipyramidal transition state. And what happens is, essentially, you can see that we are forming a new carbon nucleophile bond, and we're facilitating the removal of the carbon, leaving group bond. And it's trigonal bipyramidal because we see we have a kind of like this trigonal, prism orientation in the center, like this triangle here with the 3 substituents. That's the trigonal portion. And then bipyramidal because there's one point here and another point here. So if you just kind of looked at that, that would be a pyramid, okay? And on this side, that's another pyramid. So it's a triangle in the middle, bipyramidal. Okay, that's kind of where that name comes from. And essentially, we get inversion of configuration. So let's kind of look at an example of that. So let's say I have, let's say the starting material, and I'm subjecting it to NaCN and DMSO, okay? So essentially, what is my RNS configuration of that starting material? What do we think? Okay, what do we think is the configuration of this starting material? Yeah, I get R as well, okay? So then that incoming nucleophile we know is going to come in and attack on the back face of this molecule, okay? And it's going to facilitate that removal, and you basically get, we just said based on pure sterics, that we're gonna get the cyano group coming on a dash. But now let's assign RNS configuration here. Okay, so what do we think? What do we get? What do we get? S, good. This is an S configuration, okay? So, this is priority 1, that's priority 2, that's priority 3. We trace that, we get R, but remember that hydrogen is on a wedge, so you have to remember to flip. So that's really S, okay? So you do get this inversion of configuration, and it's a direct consequence of going through this intermediate. When this nucleophile comes in, you push these bonds over, and it causes you to get a new configuration. In terms of the stereochemistry for Sn1 conditions, what we have to consider is we get racemization typically, not always, but we typically get this racemic mixture if we have a chiral center present. So an example of that would be, let's just do this, and let me do, I guess, yeah, let's just do this. Okay, something like that. And let's subject that to ethanol, okay? So clearly this is Sn1 conditions. We have a really substituted starting material and a relatively weak nucleophile and protic solvent condition. So that all tells me Sn1. So the rate is dependent on that leaving group leaving. So we go through this, carbocation intermediate. And what happened was we go from sp3 to sp2. So you're chiral and then you're not chiral. And remember, we have this unhybridized p orbital, okay? So we get, attack at the front or the back face. So we get two, typically if this is a chiral material, we get that, and we also get that. So you get racemization, or this racemic mixture, okay, racemic. Okay, those are the two main considerations for stereochemistry. And the last thing we have to talk about is other, so I'm just gonna redraw that down here. This is other considerations that we need to consider. Okay, so what else do we need to think about? Well, Sn2 reactions are really governed by, steric factors. So let me just continue this down. Sn2 is really, governed by sterics. So we know that the less sterically hindered thing is the best for Sn2. So really, you need to ask yourself this key question, and I'm gonna write it in red. Okay, so can the nucleophile, okay, approach the reactive carbon? And I'll move this up if you can't see it. The reactive carbon, or is it hindered, by subs? Okay, so essentially here we are. So what am I saying? Well, can that incoming nucleophile, okay, approach the reactive carbon, meaning the carbon that bears that leaving group, or is it hindered by substituents? That's the main question you really need to ask yourself, because if it's not hindered, then we can do the Sn2 because it's governed by these steric, properties. We're limited to these primary and secondary materials. When we're in Sn1 conditions, what we can think really about is carbocation stability, because we go through that main intermediate. So, essentially the question you want to ask yourself over here is, do I have a sufficiently stable carbocation to allow for a nucleophilic attack? I'll rewrite this, nucleophilic attack. Okay, let me explain that a little again. So basically what you want to ask yourself when you're looking at your starting material or that intermediate that might form, is that carbocation stable? And if it is stable, does it allow for the nucleophilic attack? So these are all things that you should be asking yourself. This is pretty much a good summary of Sn1 and Sn2 pathways. Okay, Caroline, so Sn1 doesn't have to attack opposite face for stereochem. Exactly, it does not. It will attack the front face and the back face. Okay, yes, exactly. Because it's sp2, you have the front face of that orbital, the back face. Can I show oh, sorry, yes, here's the bottom. So just other things you want to think about. Sn2 is really governed by steric properties. Sn1 is really governed by, carbocation stability, which you can say is technically also sterics, but we'll say like more, okay? And here this would be less. Okay, that's kind of the goal there. What does say nucleophilic next to nucleophilic bond? Yeah, so this says, do I have a sufficiently stable carbocation to allow for a nucleophilic attack? This says, can the nucleophile approach the reactive carbon, or is it hindered by substituents? Okay. So everybody good on this summary? And you can take a screenshot maybe. Here, I'll do two phases here. This is the beginning. Okay, so the first considerations, I guess, maybe I'll just put it there. Take your screenshot. And then just like the last parts of that. Okay. So I think we've spent a decent amount of time now talking about Sn1 and Sn2 conditions. So now it's actually time to talk about the E1 and E2 conditions. So this is kind of cool. So essentially, let's just take this classic example. So we have, just like plain cyclohexane, and we'll add this bromine substituent, we'll add, this proton on the adjacent position, it's already there. And let me basically subject it to, this condition. Okay. And let's just say, so I'm going to do two different situations. So, okay, so same reagent. Okay, but what I'm going to change is the main solvent. Okay, so we clearly have a strong nucleophile. Okay, we also have a secondary, starting material. So that's interesting, right? So what are you guys thinking right now, just from the start? Strong nucleophile, we have a secondary, starting material. What do we think? What reaction pathway? Based on what we know so far, Annalise. Sn2, good, yeah, okay, you got it. So basically I'm thinking Sn2, so that's probable. And in order to ensure that I'm going through Sn2, what solvent should I have here? Aprotic, right? So any of the aprotic. So I'm just gonna rate aprotic, you guys got it. Okay, so essentially mechanistically what that looks like is this, source of electrons is gonna hit that reactive carbon and facilitate the removal of that leaving group. So essentially you just get the nucleophilic substitution product, okay? So that would be something that looks like, this and that, okay? But generally, nucleophilicity also parallels basicity, and that's something that we're gonna really see today. Nucleophilicity generally, I'm gonna say this word generally, parallels basicity, and that's important. So if I call that a strong nucleophile, I can also call it a strong base, right? Okay, that's basically what I'm saying right here. So in this situation, we were going with, let me write this in another color. This would be a strong nucleophile. And these under this solvent conditions file. Okay, under this situation, we're going to get a strong base. Okay, does anybody know how I can make sure that this solvent is a base and not really a nucleophile? What's a way to do that? Okay, remember, think theory. This is all about theory. So if I want to decrease that nucleophilicity but maintain the basic properties of it, what can I do? Has to do with the solvent. Protic. You want a protic solvent. Yeah, you guys got it. Okay, so it's protic. So remember that whole logic where the protic solvents give a little bit of those protons off into solution where the nucleophile gets slightly protonated and it decreases the nucleophilicity a little bit. So if I put these under protic conditions, I'm not going to actually get the Sn2 product. I'm actually going to get something called the E2 product. Okay, so what happens is it's kind of the same logic here, and I'm going to draw these mechanistic arrows in blue. So because the nucleophile isn't as strong anymore under these protic conditions, what can happen is that the lone pairs on the oxygen can remove a proton that's adjacent or nearby, so something like this, okay? That electron density between the carbon and the hydrogen gets donated into the ring, and then it facilitates the removal of the leaving group. So, now you get actually an alkene, interestingly enough, from that starting material, okay? So this is kind of like why this is a very tough chapter for a lot of people. It's really 4 reactions, that's it. But it's like knowing which one goes under which conditions, okay? And it's all logical. You have to really think theory. Okay, so that's kind of a good introduction to E2. But first, we're gonna just talk about E1. I just kind of want to prove to you that we get very similar, reactive conditions, but that solvent really changes everything, okay? So this is just a really important point to make in the beginning. Right? So let's kind of back up for a second, and let's talk about E1, okay? I think that's easier to talk about first, okay? So this is the same thing with unimolecular. So by that one, it means unimolecular elimination. Sounds so dramatic based on the name. Yeah, Charles, could you explain what the protic solvent does to decrease the nuclear velocity? Perfect, yes, I can. Okay, so let's give an example. I'm gonna do this, just flip over. Okay, so essentially, let's do that under, let's just say DMSO. So this is DMSO, yes, DMSO, okay? That's my nucleophile, and let's do the same conditions with water. Okay, so what happens is water can solvate this anion pretty well, okay? So what happens is that essentially, if we consider dipole moments, you should imagine that we're going to have these ends of the molecule solvating this, basically negative charge. Remember, it's partially positive here, okay? So because we have all of these water solvent molecules kind of surrounding this nucleophile, and some of it even actually gives off a proton to make it hydroxide, so it really decreases the nucleophility. All of this is happening in solution. So we have a lot of interaction with this nucleophile that we don't like. Okay, but here with DMSO, none of these protons are sufficiently partially positive or, acidic to do that transfer. So this is quite literally, I can kind of almost draw a force field or a bubble around it, and it's not really going to interact with the solvent that much. So because we don't have these interactions, this is why this is a good nucleophile. This is why this is a slightly weaker nucleophile. And we can exploit that property or this manipulation to promote this, Sn2 or E2 product. So it's kind of cool. It's really practical. All right. So that was kind of my answer. Does that help you, Charles, a little bit? All right. And Elise, do we ever produce a picture of E2 Sn2 or exactly? So we're going to see today it's only Sn1 E1 together or Sn2 or E2. Okay. And I'm gonna summarize that all on a nice chart for you. Okay, Caroline, should we memorize the idea of being a strong base when a pK is over 11, strong nucleophile? Yeah, we're going to talk about those things. And yeah, I would not say memorize is the wrong word. Just know that the pK of conjugate acid over 11 is important. But yeah. And Elise, mixture, I think we got you already. Yeah. Okay, cool. Unimolecular elimination. Okay, so essentially this is actually really easy. So the E1 is fine. So let's just take this generic example again. We typically stick to, this really substituted starting material, and we're just going to put it under typical Sn1 conditions. So I'm just going to say maybe water. Okay, so what happens is that, what is this? Let's classify this nucleophile. Is it strong or weak relatively? What do we think? Weak, right? So this is relatively weak. Okay. But we know since it's a nucleophile, it also is a base, right? So it's a weak nucleophile and a weak base, okay? So relatively weak nucleophile and relatively weak base, okay? Those are two things you have to recognize. It's a nucleophile and a base, okay? So let's just consider the nucleophile part. What does the nucleophile do in this reaction? Well, this looks like Sn1. So essentially, let's just draw that main, rate determining step where we get, and I'll just draw this. I'm just trying to bring back all the main concepts here. So we get this carbocation intermediate, it's stabilized, it's pretty good. And then what we could have under this, nucleophile definition is with the water acting as a nucleophile, where those lone pairs come in, fix that deficiency, okay? And we basically get, this hydrate, and, you do a step, you assume the excess solvent, I'll just skip that step, and you get, an alcohol synthesized, okay? So that would be the SN1 product that we have seen. And yes, under these reaction conditions, you should write this SN1 product 100%, that is happening. But because it's a nucleophile as well as a base, we have to consider how this water molecule, when it acts as a base, could lead to a different product. So what happens is the same rate determining step is happening. So we're gonna get this carbocation intermediate. But now what's gonna happen is a slightly different set of mechanistic arrows. So basically what we're calling, whatever that carbon is that bears this leaving group, that's my alpha carbon, okay? And it's just alpha because it's the first one in the Greek alphabet, so it's basically saying that, oh, this is the main carbon, the most reactive carbon, the one we're really looking at. Okay, so then for each adjacent carbon you move therefore outwards, you call it beta, then gamma, then delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu, xi, omicron, pi, rho, sigma, tau. Yeah, all the way down. So essentially what happens is that this is now going to remove one of these protons, okay? So these lone pairs removes the proton, okay? Again, that electron density gets retained into the linear structure to fix that deficiency. And you're really gonna result in this, alkene material. So whenever you have SN1 conditions, you always have E1 conditions. Okay, so we didn't talk about that before, so we've only been, SN1 versus SN2. So we were wrong before. All of those old questions you can now go back to where, it said ignore elimination products for now, and you can actually answer and add in those elimination products because we weren't telling you the full picture. But you can see that nucleophiles can act as bases as well, and you have to consider both of those products, and these do both exist in solution. Okay, are we kind of clear on the concept for SN1 and E1? And we can go into a few examples right now. Okay, so essentially we're going to start with, let me see where we are. Let's do a relatively, okay, so let's start with this one. So an example. So I am on, I'm just going to go back to some of those old problems. So I'm on page 104. I'm looking at letter L. So we have this kind of bicyclic structure. Okay, we have a carbox, no, it's actually an ester, excuse me. It's an ester leaving group, and here we go. And we are going to give this to some sort of vial. Oh, sorry about that. Okay, so we're here. Okay, so essentially what we're having is we have this tertiary, quaternary, actually, starting material. Okay. Oh no, excuse me, tertiary. I'm not saying quaternary. Tertiary starting material. And what happens is that leaving group is just going to leave on its own. We know that. Okay, so essentially you lose that absolute configuration now. So you're just left with this carbocation intermediate, okay? Oh, excuse me, with this methyl group there. So now we're sp2, okay? So that thiol, group can come in and do nucleophilic attack, and we get racemization at that position. So essentially, this is the SN1 product. Okay, so this is the SN1 products, the racemic products that you get from that way. But since we now know what E1 also happens because it's a weak nucleophile, weak base, we have a whole bunch of beta positions that we can choose from. Okay, so we have beta, beta 1, you have beta 2, and you have beta 3, and you honestly get a mixture of products there. So let's think about this. You can get removal of the proton at the beta 1 position, and let's see what that product looks like. So if I remove the proton, donate it into the ring and fix that deficiency, I can essentially get, this alkene right here, okay? Oh wait, I didn't draw this right. I'm sorry, that methyl group's over there. This methyl group's over here, I just noticed that. I'm sorry, guys. I can redraw it for you, hold on. So essentially, I move that methyl over. So we have the methyl there, okay? And this is my main carbocation intermediate. I'm sorry, ignore these before. I'll just fill in the SN1. So the SN1 products would be, okay, and then here's that other ring. Okay, I didn't see that. Okay, and then this one would be dash S and that methyl. Okay, so we're there. And those are my SN1 products. But then back on that carbocation intermediate, we have 3 beta positions. We have beta 1, we have beta 2, and we have beta 3. Okay, so which one am I going to choose? Okay, so pick one in the chat box. What do you guys think? Beta 1, beta 2, beta 3. Which proton are you on? Okay, you guys got it, beta 2. And the reason that is because we have some sort of reagent selectivity thing to consider here. So essentially, you know, I can remove any of those protons, but let's say I remove beta 3. If I remove beta 3, this is their resulting alkene. Okay, what's the classification of that alkene in terms of substitution? Secondary, right? That's a di-substituted geminal alkene, so di-substituted. Okay, let's remove from beta 1. So if I remove from beta 1, I know I'm running out of space, sorry guys. If I remove from beta 1, I basically get that. Okay, what's the substitution of that alkene? Tri, right? Okay, so now let's do it from beta 2. If I remove it from beta 2, sorry, running out of space, what do I get? Tetra, right? Boom. So you do have all of these technically forming in your solution. However, which one's your major elimination product? Tetra. Boom, you guys got it. So on your test, all you would say is the tetra one, okay, this tetra elimination product, and you would also show your 2 major stereoisomers from the Sn1 pathway. Okay, so this is just adding on a little bit more information, nothing crazy, okay, but we already know alkene stability. You guys know that. So you basically want to eliminate in a way that you get a more substituted alkene. Okay, that's favorable. And you already know Sn1, all right? Exactly, the others do still form. They're considered minor products. So Dr. Pearson, we're like, what's a potential minor product for the above reaction? Well, this di-substituted alkene could be one, this tri-substituted. So you can basically say like, oh, this is maybe 40%. Here, let's do, this is 20% of my solution. This is another 20% of my solution. This might be 40% of my solution. This might be 10%, you know, and that might be 10%. So you see the relative abundance. This whole thing adds up to 40. This is probably 40%, you know, and that's probably the remaining 20% of my solution, okay? That's just a regular, you know, I just threw out those numbers in there, but that's how you should have imagined it. Exactly, you got it. Lilas, everybody read what Lilas just said. So essentially you never have to like know when is E1 happening, because if you're able to know when Sn1 is happening, you always draw that E1, okay? Always. Okay, and I also want to just talk about a special name that these get. This reagent selectivity thing that's happening right here, this is known as the Zaitsev product. It's another German thing, I believe. So Zaitsev is just a more stable product. It's the more stable alkene, whereas any of these are the less substitute. That's called Hoffman, the Hoffman product. Okay, so it's just a name. You know, we used to have Markovnikov and anti-Markovnikov. This is Zaitsev and Hoffman when it talks about alkene stability, okay? I think we're good there. So let's move on into, is there a minor for Sn1? No, there is not a minor product for Sn1. Okay, good question. All right, let's move on to E2. So how do you guys feel at E1, right? Nothing new. Just make sure you consider that potential basic product that forms. Would there be, if there was a rearrangement, would there be? Yeah, I guess you could say that. Yeah, you would always get a slight amount of, you know, that minor product before rearrangement. So yeah, you could argue that as well. All right, so that's E1. Okay, so E2 is not fun, and I'm just going to be honest with that. So this one's pretty tricky. How can I really help you guys with this? Essentially, what you need to know is a couple of key pieces of information. I'm just trying to get that pulled up for you. Here we go. Sorry. Okay, so what's happening with E2? So, oh, and sorry, one more thing about that last that we were just talking about. So here, let's draw a rate law for the E2 pathway, excuse me, E1 pathway, okay? So here, rate is dependent on some sort of generic constant, and then what do you think? Is it, you know, dependent on 2 things or 1 thing? I hope you guys are saying 1. Yeah, 1, good. So it's just the concentration of that starting material to the first power. So the exact same rate law applies to E1 as it did with Sn1. Okay, so something to note. Let's move on to E2. So something we need to know about E2 is that it's bimolecular substitution. Okay, so this is the, and again, you guys might see the term beta elimination. You guys now know where that beta comes from. It's just talking about removing a proton from that one adjacent carbon from before, okay? So essentially, let's take this example of, again, it looks like it's going to be an Sn2 reaction. So let me just take this example, okay? And I'm going to subject this to now sodium hydroxide and water, okay? What's the question here? This is, Keisha, what's your question exactly? If you want to elaborate, just let me know. So essentially, this is kind of looking like an Sn1 or E1 pathway. Oh, thanks. I'm like, oblivious sometimes. Elimination, thank you for that. This is bimolecular elimination. Okay, so essentially, we have that same, what looks like an Sn1 pathway or an E1 pathway in terms of that starting material. However, we definitely have a lot of different things going on here. Well, what do we have now? Well, we have a strong base, right? Okay, strong base, okay? Strong base, and we can also call that a strong nucleophile, okay? So let's just use logic here, okay? Steric argument. Is this sterically crowded, that alpha carbon? Is my alpha carbon sterically hindered? Oh yeah, for sure. Okay, so if it's sterically hindered, do I think that my nucleophile can really attack or reach that carbon? No, right, no, not at all. So what happens instead is we're gonna have this hydroxide act as a base because we can't really exploit the nucleophilicity here because purely because of how sterically hindered this is. And since we have, based on it being, the trends are paralleling, if it's strong a nucleophile, it's a strong base, well, the base is fine because what we can do is we can actually remove one of the protons. Okay, so let me call this beta, and this is one of the beta protons, okay? And what we could have is that hydroxide anion, it can't be a nucleophile in this case because of the sterics, but what it can do is it can still be a base, remove that proton, push it in, and remove that bromine, okay? So essentially you can get this elimination product, this E2 product, okay? So now you have to kind of note that Sn1 and E2 can be in composite, and Sn2 E1, so together, is in competition with E2, okay? And that's kind of like the hard argument here. Excuse me, I meant to say Sn1, okay. Sn1 E1 is in competition with E2, and that's like the hardest thing for everybody to grasp like every semester. So essentially, you would know it's Sn1 and E1 if you had Sn1 conditions, meaning you had that weak nucleophile, like we talked about, okay? Weak nucleophile, maybe protic conditions, things like that. So this is Sn1 and E1 pathway. In this situation, we have a strong base or stronger nucleophile, but I don't want to say nucleophile because we're exclusively getting this base because it's a substituted product. We can't exploit those nucleophilicity anymore. So an example of this would be like, that versus that, okay? So this is a strong base, strong nucleophile, but we eliminate the nucleophile part because of, the sterically hindered starting material. And then here, this would be a weak nucleophile, weak base here. Maybe I'll just keep both. Weak nucleophile, weak base. This is strong nucleophile, strong base, but we canceled out nucleophile, okay? So essentially that's the main key here. So for me, when I'm trying to teach this to you guys, all I'm gonna say to you this is when you have Sn1 conditions, you guys know how to recognize that at this point. When you have Sn2 conditions, you know how to recognize that at this point. When you have E1, you also know how to recognize that at this point. What I say every semester is when you have conflicting pieces of information, meaning up until this point, yeah, I have a very substituted starting material. And then, here I have a strong base. Okay, that's weird. Normally for really substituted materials, I have a weak nucleophile, weak base and protic condition. So when it's conflicting, meaning it's tertiary but strong, or maybe like really another variant of that or anything like that, it's basically going to give you the E2 product, okay? And if that didn't make sense, I'll catch you on examples, okay? I promise. And I think I have some questions to answer in the chat. Let's see. Okay, here we go. Could we also say that since it is 3, we don't do Sn2? Roxana, is this an older question? I don't, what's the 3?
We don't compete with Sn2.
Wait, say that one more time. You chopped out. I didn't hear you exactly.
I just realized that we don't compete with Sn2.
Correct. Yeah, we don't. Okay, good. Even if that was a protic, would it still be E2 because of the sterics? Even if it was a protic, sterics. Even if it was aprotic conditions, yeah, it would still be, it would still be E2. Does E2 have protic or aprotic conditions, or should it be any one case by case? It really is case by case in this example. That's why this is a very hard chapter for people. We saw that, initial situation here. This is why I introduced this. So when you look at this example, we had, that same strong nucleophile, strong base. This is a secondary, so it's not as crowded. So this is when the solvent really mattered, okay? So, when we were, with this example, the solvent really, I could say protic or aprotic, and it really wouldn't affect anything here. It would still get the E2 product, but in this situation, it mattered because you're not as sterically hindered as before, and now the guiding principle is protic or aprotic, okay? So yeah, it does matter in some cases, it doesn't matter in all the cases. That's why it's not so cookie cut, all right? So that's E2, okay? That's E2 so far. So again, let's just do some examples of this. So let's see. Let me see where my problem's at. Here we go. Okay, so let's just take this example. So we have, I'm on page, let's see, on the student workbook, I am on page, okay, I think it's, what's the number here? 105, page 105. And we're gonna do A, okay? So this is the example, and we're subjecting it to potassium methoxide and ethanol, okay? So what do we think here? When I dissociate that potassium, I get this, looks like strong nucleophile, strong base, okay? Strong nucleophile, and we have a strong base, okay? So what happens is like I have a relatively, I have a secondary, starting material, okay? So right now I'm thinking, okay, secondary is my gray area. I have a strong nucleophile. I'm thinking Sn2, right? I would think Sn2. Oh, but wait, this solvent, okay, this solvent is protic, okay? So what happens is it kind of decreases the nucleophilicity of this a little bit, okay? So I can kind of just say that this is actually really gonna be a strong base. Also, something to note, before we were kind of predicting Sn2 products. Something we need to add now is that the pKa of the conjugate acid has to be greater than 11 for E2, okay? That is weird. Dr. Peterson could give you pKa values on this test. So essentially, if I were to look at the pKa of ethanol, the pKa of ethanol is definitely greater than 11. So that's why this is gonna go through an E2 mechanism. So if you needed these, we would provide them for you, don't memorize. But just something just to keep in mind that these alkoxide anions, I've been saying that a lot now, the alkoxide anions are a great example of this. Water is another, the hydroxide anion is another example of this, So any of these oxygen containing, anions typically are gonna follow this E2 pathway, okay? So you don't have to memorize them all. You can just kind of have a general idea that anytime I see these oxygen-based, bases or nucleophiles, they're gonna pretty much promote the E2 pathway, especially under protic conditions. Right? So that's why that's happening. So essentially we have a couple of beta positions, we can remove from this beta position, beta 1 maybe, and we could also maybe remove from this beta position, beta 2. And which one should I pick, beta 1 or beta 2, based on just substitution? Beta 1, right? So if I remove, this proton up here, donate that into the ring, that facilitates the removal here, I exclusively am getting E2, okay, here. Okay, and it's the substituted, this is the Zaitsev. Okay, but now let's say Dr. Peterson is asking on the test, I want you to show me the Hoffman product. What's a potential Hoffman product for this reaction? Okay, well, the Hoffman product would be removing from beta 2. Okay, so you would have basically this and that. Okay, that would be the Hoffman. Okay, and obviously this is the minor product, but this is the Zaitsev, the one that forms the most. Okay, so you guys can kind of see how this is a little weird. We have this competition right now where we don't really know what's going. Oh wait, did I say? Oh wait a minute. I think I know what you were talking about earlier. Roxana, were you talking about Sn2 up here? Is this what you're referring to?
Yes.
Okay, I must have not understood. Okay, so this is really supposed to be Sn2. I apologize for that. So this is kind of the classic argument we're seeing here. We don't know if in the secondary position, is it going to go through the Sn2 or the E2 pathway? I apologize for that. I know this is tough and I don't want to make you more confused. So Sn2 versus E2. So essentially we have that same secondary material. And then now what we're seeing is like, oh, is it going to go through, that nucleophile addition pathway And it's not because of this protic solvent going on here and also the pK of this conjugate acid. But if it was aprotic, yeah, we would definitely expect Sn2, okay? So that's an example. That. Okay, can we also see, here we go, what's going on here? So if it was aprotic conditions, exactly, yes. And Elise and Caroline, yes, those are both gonna be Sn2 products. So let's just draw that. Oops, let's just draw, let's just do OET negative. Let's just say DMSO, and then you would get, you know, backside attack, OET. Boom, okay, Sn2. Oops, sorry, all over the place. Sn2. It is a strong nucleophile. Negative charge, so it's strong. Does that help, Charles, a little bit? All right. During our comparison. Well, yeah, that's why I make these notes as I go, so it's not the best. When I was talking about Sn1E1, that's what I was referring to. Sn1E1 was referring to the weak nucleophile, weak base. Okay, but clearly down here, what we're talking about is an Sn2 argument versus E2, and that's what I was kind of referring to. Typically, we get this classic example, Sn2 versus E2, or sometimes we could even get, actually, maybe you could say that. It's basically all of these compared to E2. Let's do that, okay? Again, I'm not a professor, but I try to do my best with you guys in explaining these things in the way that I think it's easier. So are we good now? It's either Sn1 and E1 sometimes, which we saw like this situation versus E1. This looks like it's going through Sn1, E1, but it's really going to go through, you know, I'm sorry, it's really going to go through E2 for reasons we just talked about, you know. But here, this was an example of Sn2 versus E2, and it goes through E2. So this is the devil, basically. This is the one that like everybody's like, oh, I hate this one. Okay. Thank you. So you're sweet, Madison. So basically what we want to consider is one more thing with this elimination example, and it has to do with these like cyclic systems. So a really important question, and you're 100% going to be tested on the exam with this, is going to be question, where is it? That's question 10 on page 107. So everybody go there right now. Okay, so question 10, and essentially you have this kind of scenario going on. And I wrote this over the summer, and Dr. Pearson asked it that same semester on the test. So definitely know how to do this. So we have this kind of crazy branched, it looks like, oh God, it looks, basically I'll draw this in line angle. It's supposed to be 1, 2, 3, that, so it's really long. And then you just have the protonated version of that solvent, okay? So essentially what we're gonna think is, you know, this is a relatively strong nucleophile, strong base, right? Strong nucleophile, strong base, just from comparison, just looking at it right now, strong nucleophile, strong base because of that negative charge. But because of this solvent effects, this solvent, it's gonna give a little, it's protic, it's gonna reduce the nucleophilicity of it a little bit, but not the basicity of this. Also, what I consider this base to be, you know, let's just leave it at that. So essentially this is a secondary, you know, starting material, okay? I have a strong nucleophile, strong base, but we ruled out the strong nucleophile because of the solvent. So now all we're left with is this strong base argument, okay? So we have two beta positions that we could probably eliminate from, beta 1 and beta 2. So let me draw in those protons, okay? So which beta position, beta 1 or beta 2, should I, let's just say that, which proton should I be removing from to form the more stable alkene? Beta 2, right? It's obvious that I would go right to beta 2. I would think to remove that proton, donate it into the ring, get a tri-substituted alkene, but that's not what we're really going to get, and you see that. So the classic, what this is showing you is that the Zaitsev product is what you're typically used to. You should get this, you know, really substituted, you know, alkene, okay? So that's the Zaitsev. But according to what the problem says, is we actually get 0% in solution, and we get 100% of the unstable, you know, the Hoffman product, which is kind of bizarre, right? Why am I getting the Hoffman product? 100%, okay? And it actually doesn't have to do with, this isn't a bulky argument, okay? And we're gonna talk about bulky right after this. This isn't a bulky argument. The argument here is that you have to have this thing called anticoplanar. And I said to you back when we did chair conformers in chapter 3, that it was gonna come back for 1 second in chapter 9. And I don't know if you guys remember that, but I did say that. It's gonna come back for 1 second. You have to draw a chair, okay? So let's just draw chairs. I know you guys are rolling your eyes, probably virtually. And let's just kind of see what these chairs look like, okay? So we know that, let's just recap. On 1, I'm pulling it up. So does that look like it's gonna be up? No, okay? So I'm just gonna do these fast because I assume you guys are good at this by now. Okay, on 2, we have 2 protons, so here and here. And then we're just going to 6, so the trend on 6 should be down, so that our proton is down, and then this is an equatorial isopropyl. Okay, so my leaving group is this. This is my leaving group. And then the proton that I'm removing is clearly, based on this problem, going to be from the Hoffman position, so that's this beta 1 over here, that's beta 2. So in beta 1, your proton and your leaving group have to be 180, or anti-coplanar. Okay, and it's not really obvious in this kind of fashion. So let me draw another the ring flip of this. Okay, so essentially you get that, and then that was position 1, and then this would be beta 2 over here. So beta 2, you have this, and you have that. Okay, so this is just how I'm numbering it. And essentially, this is all I really care about, carbon 1 and carbon 2. And essentially, you can look at this leaving group and this proton, and they are 180 trans apart from each other. So what is happening in real time is, let's just call it RO for the space, R is the rest of the chain. And what's gonna happen is it's gonna remove that proton, donate it down, and kick it off, okay? And you guys don't know the full reason for this. I'll just tell you that the full reason has to do with the orbital overlaps of the leaving group, the nucleophile, and the proton. So this is a perfect arrangement that all of these electrons can be transferred in one kind of quick fashion. If it wasn't in this orientation, then you couldn't, do it as quickly. So there's this orbital thing that you don't need to know about for the course, but you basically can't remove. And let me just show the other proton for beta 2. Now this isopropyl group should be up, okay? So that makes this equatorial proton. This proton, which is beta 1, is not 180 degrees from, or 180 anti from this leaving group. It's equatorial, and that's axial. So no, this cannot be removed. It has to be in this weird position due to orbital arguments that are beyond the scope of this class. Just know that you need to have 180 degrees. So this is kind of a trick question. It's gonna be asked, okay? So just remember that you have to have in ring systems, it's only in ring systems, this kind of weird orbital arrangement where you are anti-coplanar. That's the word, coplanar, okay? Any questions on that? I know it's weird, but just another thing to keep in mind. Great. Oh yeah, Caroline, what's your question?
So when you first drew the chair, like the ester group it was equatorial first, so you had
Correct.
to change it to be axial to see this?
You could, I guess, have seen it technically here. You could have seen that this is technically 180 from each other. But I just think like this is very clear. When they're axial like that, I would just always go to the axial, because this is just really showing how that it's trans, up and down. That's just how I visualize it. I guess you could have seen it from here, but yeah, I would really go to the axial. I would just say for you, Caroline, just always go to the axial leaving group chair conformer, okay? And then everything else should make more sense. Right.
So after you go axial, then you'll see which
proton is also. Yes, exactly.
Okay. And are these the only rings or conformers that we have to draw, or no?
What do you mean? Are there more chairs to draw for this?
Yeah, that's what I mean.
So you don't have to draw any chairs. Actually, maybe the question does ask for a chair. Yeah, okay. So you would really have to just draw this one, and just show that, this axial and this axial group are, 180 from each other. That's it. Okay. And it's only in ring systems. Yep, I thought we had to rotate for other molecules too. I meant chairs. Chairs is only in ring systems. But yes, you're right. So sometimes we see Newman projections with this as well, Annalise. So an example of that would be like, let's say my leaving group is here. And let's say I have, that, and let's say I have, let me just say I have this. Okay, so right now, if I were to draw a Newman projection, let's just say I'm doing this in the same exact condition. So this double kind of line thing, it just means the same exact conditions from above, that weird alkoxide anion. Okay, so essentially when we do this Newman projection, I see that I'm gonna draw that as ethyl, I'm gonna draw that as the proton, I'm gonna draw that as the methyl. Okay, and then on the back carbon, I have the methyl going up, I have the chloride, it looks like, going to the left, and then I have this proton here, okay? So when you're thinking about a potential base so this is alpha, so we have beta, and we have beta. I want beta 1, clearly, because it's gonna give me the more substituted alkene. Oh, sorry. Okay, So I want beta 1 because it's clearly the more substituted position to give me that better alkene, right? Not beta 2. So I'm looking at the beta 1 proton, or the proton on the front carbon. Okay, so the proton on the front carbon, I'm just going to circle. That's this guy. And then the leaving group is this guy. So those need to be in that same anti-conformer that you are used to with Newman projections, okay? So what I need to do is I need to rotate the either back carbon or the front carbon. I'm going to rotate the back carbon, let's just say 120 degrees, so that it replaces where that proton is, okay? So if I were to do that 120 rotation, the front carbon stays the same, okay? So the hydrogen, the methyl group, okay? And then on the back carbon, you have, your chlorine shifting here, your hydrogen shifting here, and then your methyl shifting here. Now that proton on the front carbon and the chlorine in the back carbon are in the right conformation to do that, okay? So essentially, what you want to do here is you want to rotate around this bond twice, okay? So do one move at a time. And remember my WPD, okay? Now that I'm in like West Palm Beach or whatever, I just call it West Palm Beach Department or something. I don't know. Maybe that helps you. Okay, so what you want to do is rotate one thing at a time. So essentially, I'm just going to draw the same framework. Okay, so I'm going to draw the same framework. So we have that. The wedge thing is going to go to planar. Okay, so that's now a planar ethyl. The plane thing now goes to a dash. So we have a dashed, oops, doesn't go there. We have a dashed methyl, okay? And then that dash goes to a wedge. So now I have a wedged proton. Okay, so that was one move, okay? I have to move one more time, okay? So now that wedge goes to plane, okay? So let me draw it over here. So that wedge goes to plane, okay? That, that planar thing goes to a dash. So now we're that. And then that dash goes to a wedge. So now we're here, okay? Let's draw a Newman with this, new configuration just to make sure that I got what I needed, okay? So we're down, proton here, methyl here, ethyl. Back carbon is up, methyl. It looks like here, chlorine, and I know I messed up already because look, that chlorine is not where this hydrogen was. So maybe I went too far. Maybe I didn't have to do 2 rounds. So let's just check that again. So I'm down, that would be ethyl for this guy. This would be the hydrogen for that guy. So you just really guess and check. Like that's kind of what I would do. And that would be methyl up. That would be the chlorine to the left. And there we go. You guys can clearly see that. Here we go. So this was actually a decent, I didn't have to do one more time. Okay, but that's okay. Even if you mess up and you keep going, Caroline, clearly I messed up by saying rotate twice. Even if you mess up, like just draw the Newman and it has to correspond, and it didn't. So I went backwards. Okay. So here I am, and this is the right conformation for elimination to happen. Okay, so what you can do is you can imagine that we have like a base. I'm just going to call it OR minus. Okay, it's going to remove this proton, donate it into the ring, and move that. Okay, so we get this kind of This is a situation where we're going to be trans to each other. Okay, but there could also be situations where you could see a cis arrangement happen. Okay, so you just always have to have those 2 groups in E2 anti-coplanar from each other. All right, so this would be an E alkene. There are other examples where you get Z, to get a Z alkene, let me kind of manipulate this problem. Maybe I'll find another one as we go. Okay, so I have one more thing I want to talk about, and it has to do with bulky bases. So up until this point, we all know E1, right? We're all good with E1, that's easy. Every time you have Sn1 conditions, you have E1, okay? And Roxana, no, you only put the major one. So whichever one is major. Yes, E1 is great. We love E1. Then for E2, we have competition. It could either be the Sn1 E1 competing with E2, or it could be Sn2 competing with E2. And how did I know that? So let's just say this would be a situation where I'm competing because it's secondary. So I would say secondary is Sn2 versus E2. But when I'm tertiary, that's an Sn1 E1 versus E2. Okay, so we don't know which one's going to prevail. We can promote it down E2 if we, make this a, how did I do this before? I forget, where's my other problem? You can promote it down, there we go. Where did I show that? totally losing my train of thought. Is on the other page? Ah, here we go. Yeah. So you could promote it down the E2 pathway by using a strong base